noticed from finding out for class of value, seems like the hot topic is computer vision. I mean, did you see how quickly that class just like pointed out? Wait. And there's so much that you can actually be able to do with audio despite the advancements that have been made with machine learning algorithms in the last couple of years. For those of you who do not exactly know audio data, it can be represented as a series of floating points to imply frequency waves. And one of the subproblems within audio machine learning is the subproblem of the speech recognition and the high accuracy of automatic tone classification of words without the contextual speech, which is quite a unique problem that hasn't been solved yet, but there is still some applications for it. We still have yet to improve the performance of this, and we can actually imply real-world use, such as using it with color implants with deaf children so that they can actually process the tone better. And one of the languages that is very tonal is Mandarin. For those of you who don't know, I actually am learning the language. And what's very interesting about this language is that you can use tones to differentiate between characters with the same syllables. For instance, this character here is called Dao, which has this flat tone and kind of a sing-songy tone, and that translates to the word night. And you got this other character called Dao, which has a dropping intonation, and that means to arrive. And in Mandarin, there are these four tones, which is the flat tone, the rising tone, a dipping tone, and a dropping tone, which is demonstrated with these charts. And you can use them in combination with any number of syllables to give you a great number of potential words. So my project will implement 36 tokens, 9 syllables with these 4 tones, and you can find that there can be even much more to work with. For my input, I'm going to break down audio signals. I'm going to map audio signals to these tones and their syllables. So you have your input for your audio and the output, the English written. So that would be DA01. So I start off with 25 millisecond size audio chunks at 44.1 kilohertz, which means that there will be 1,102 samples from these 25 millisecond audio signals. And we can say words or characters in sort of like slightly different durations. So I account for that by adding padding to any short characters, or I would truncate any unusually long characters to match the 25 millisecond inputs. It would start off as a continuous signal, but I would teach it to recognize any words by using a moving average. So pretty much starts off as silence, or when you start to speak, your tone is kind of a little softer. So as you speak, you have more of your sample values tend to be higher. So if you use higher samples, it would send the moving average up a threshold, and that threshold would indicate the beginning and end of a word, because words tend to have slight pauses in between them. From these audio chunks, I would use VHDL to extract each of these features and hopefully learn to optimize them for maximum performance. Loudness, and it works so well with Mandarin because the pitch and the loudness and the source of brightness, this tends to work better than English, where things tend to be a little more monosyllabic or monotonal. So I have each of these equations that I tend to write out as VHDL. This one's loudness, which is pretty self-explanatory. I will calculate using the root mean square. Second one is pitch, which is a series of short time Fourier spectrum. It's good for indicating the starting and ending pitch of Mandarin characters, because you can easily imply which of the 4 tones it is. Brightness is computed at the centroid of the short time Fourier transform, and can be stored as a log frequency, which I intend to do. It's usually a measure of the higher frequency content of the signal. And for my W0 at the beginning of the interval, I use that to represent the half sampling frequency. bandwidth is computed as the magnitude-weighted average of the differences between these spectral components and the spectroid, and you can see it as a magnitude-weighted average of the differences between these components. And from these features, I can actually defer several more, such as averages and deviations. And I can count up to 17 of these features, which I will use to build up my feature vector. My neural network will use these features and 2 hidden layers. Each of these layers will have 6 neurons, and my activation function is sigmoid. I will try to attempt this in Python for experimentation with other numbers of hidden layers and neurons, and use them for comparison. Future considerations. Because you can actually represent sound as something called a Mel frequency substitutional coefficient, and that's basically an array of the count of all the frequencies within the audio signal. So there's sort of like visual information you can infer here, which is why a convolutional neural network would be appropriate. I can implement the XNOR net to help improve the performance of this. Other considerations use floating points because it is a very peculiar, intricate sort of differentiation between these sample values. But obviously working with floating point is a little more trickier than fixed point. And also to try to implement training into these. This was the paper was based on, applying neural networks on content-based audio classifications. It is a little bit dated considering the current field, but this was what I was working on. Any questions?
So this is primarily a software-based project.
I was trying to apply that chip and implementing it mostly in VHDL.
You will do that?
Yes.
Oh, no. Okay. Back to the topology part. The network topology, you have 7 inputs, 17, I'm sorry. Is it done now?
Is it what?
Is it done? Complete? I mean, you can easily find some neural network online. My point is that you don't have to, if you want to implement some hardware, you don't have to do the software part. You can find some existing code. And this is a multiple level perception, not LSTM.
I couldn't implement LSTM.
No. Set a goal to a low level.
Yeah.
Make sure you can finish something. Do not always, want to achieve a very large goal. So find some existing code on this part, and then implement just naively implement some MLP by VHDL. I think this is good enough for you for this project. Make sure you can have something, and then you can implement it. For example, you change the MLP to LSTM. This is a huge plus. But again, make sure you have something to submit. Okay? Find some existing code. This is my suggestion. Find some existing code which can achieve, I don't know, maybe 90% accuracy. This is not about accurate. This is you didn't try to do some classification. You try to do some remove the noise, right?
Remove the noise.
Or identify the.
I didn't do any noise removal. Just simply like having the audio file as is. But I guess it would make sense for future use so that it can be more robust.
What's the goal of this neural network?
Classify tones.
Okay. I see.
Okay, you start off with the audio.
Okay.
And you output the.
I thought it's a regression process, but it's not. It's just another classification. Okay, that's good. Yeah, find some existing code and implement a VHDL MLP. Yeah, this is my suggestion. If you have more time, you can try to implement a LSTM. Yeah, that's all.